Welcome, welcome to the pre-recording of the first half of lecture 2 on computer algorithms 1 in the 8-week summer session. So in this first half, I will focus on the definition of asymptotic growth of the cost of algorithms. We will need this to decide which algorithms are efficient. So the first title is computational tractability, which kind of is a scary word, but it kind of indicates which algorithms can we actually efficiently run on computers. So the first half of this lecture 2 will end with some examples of common running times. In the second half, in the next pre-recording, I will start again with the examples, and then we will prove properties of asymptotic growth rates. So in the 8-week summer sessions, lectures take 100 minutes. So this is why we have structured the pre-recordings in two halves. All right, how do we define now efficiency? Well, an efficient program runs very fast in practice, but that's kind of what is fast already. So some people like seconds, other people find milliseconds they need, and other people are quite happy to wait a minute. So we need something independent of computers essentially. So this is about computer algorithms, but we try to understand things mathematically. So also, which program run efficiently? Some people are quite happy with interpreted languages such as Python. Other people really want efficient compiled code. Other people care about, I also teach supercomputing, we care about performance. So here, this is again a course focused on the design and analysis. We want to work with definitions, and the first important definition is the input size. In this course, we also study discrete problems. And you could argue that inside a computer, everything is just a sequence of zeros and ones. So everything is actually an integer. So we count the number of integers. So here we make abstractions. So integers can grow arbitrarily long. We actually do not consider the bit size. Our integers are the integers as they are. One can argue that as far as practical computers goes, this is already a definition that does not work because you cannot put all the integers in a computer. So there are integers that are so long that cannot fit a computer. Okay, a lot of restrictions and abstractions. So the capital N is an input size, and we express the cost, the running time of an algorithm in that input size. So here is the definition again, and I will illustrate the definition on the stable matching problem. The stable matching problem, which we discussed at length in the previous lecture, deals with n employers and n applicants. So there is the little n for the dimension of the problem. There is the capital N for the input size. So that is important here. So the stable matching problem is not important here other than to point at the dimension and the input size. So in our job market problem, we had on input for every employer, there was a ranking of the applicants. So every employer had ranked the applications the applicants and also the applications in order of the fitness for a job. Every applicant has also a preference for a particular type of employer. So we have a ranking, and that was expressed by integers. So in total, we had two tables. Um, Two tables, one table for the employers, another table for all the applicants. So the input size, so one table n by n employers, n applicants, two tables, 2 times n square. So the input size is twice the square of the dimension for the stable matching problem. Consistently through this lecture, I will work always with the capital N, the input size. But naturally, we would like to express our running time in the true dimension of the problem. So that is um, problematic here. Okay, first important definition, input size. Second definition is the worst case running time. So the worst case running time is the largest possible running time an algorithm can have over all possible inputs. So we've seen that with the Gale-Shapley algorithm, it can be over very quickly if there is an absolute ranking of the employers and the applicants. Then actually the algorithm terminates in n steps. Typically, there are rounds of interviews, rounds of job offers, and there are offers being rejected, commitments being broken. So the fact that the Gale-Shapley algorithm terminated was not clear, but we proved last time that at most it will take at most n square iterations. So therefore, if we want to bound the running time in the input size, we actually have that the worst case, and that's actually in the worst case, we counted the number of offers. In the worst case of the running algorithm, we have half of the input size. Now, one can actually argue that this is a time, that is a viewpoint of very pessimistic, but it's always useful to actually compare the running time with the brute force algorithm. So we did not start like that, but suppose that in the stable matching, actually now the stable marriage problem with n men and n women, we would enumerate all possible choices for every man and for every woman. So that would lead to n factorial possible perfect matchings. So a brute force search algorithm would have to enumerate all n factorial perfect matching. And that is if you can do this if you have 4 employers, 4 applicants, but obviously you do not want to do this for large number of employers and applicants. Okay, let's look at now the definition of an efficient algorithm. So an efficient algorithm actually scales. So if we double the input size, how does the running time increase? So we say that an algorithm runs in polynomial time if the running time grows as a monomial. Monomial times some constant. The constant is independent of the input size. Also, the exponent is independent of the input size. And we are studying computer algorithms here. So the number of steps is expressed in primitives, computational steps. So every step takes a constant time. So now we can define efficient. So polynomial running time algorithms are efficient algorithms. And for practical purposes, we should only consider polynomial running time algorithms. Okay, so this is our first important definition. Now, definition 3 is complicated, and we will see many examples of that. So, in it is actually a limit definition from analysis. So, we actually look at what happens in the limit. So, you can actually say a polynomial is actually, by definition, poly many monomials. And here, actually, you use only one monomial. How come? So we will prove that in this lecture why it suffices to focus on the leading monomial of any polynomial running time. Okay, here's some examples. So we have, suppose we have a computer that can do 1 million instructions per second. So in some sense, these times are a little bit outdated. You could think of a megahertz computer, or you have an implementation that runs at mega floating point operations per second, megaflops as we would say. But nevertheless, if you would scale this up to a billion or trillion instructions per second, you would arrive at the same conclusions. So if you can do a million instructions per second, then if you're a linear in the input, then you will actually not notice anything up till it gets to 1000. Then the cost would be millisecond. For 10,000, it would be 10 milliseconds. For 100,000 input size, it would be 100 milliseconds. And only when you will hit 1 million, you can do 1 million instructions per second, you will notice a running time of 1 second. Now then we have the n log n algorithms. Why is n log n there? Well, that's the best cost for sorting algorithms. Quick sort, or merge sorts, if you will remember. Then actually, often this is said to be quasi-linear, although the difference for 1 million between 20 seconds and 1 second is already noticeable. Okay, quadratic in the input size. There you see, if you are doubling the input size, and actually then the running time quadruples. In some sense, where should we look at? Well, we have from 50 to 100, 2 milliseconds to 10 milliseconds. So there was some rounding happening here. So if you multiply by 10, then the running time multiplies by 100. So you go from seconds to minutes, from minutes to hours, from hours to days. So in some sense, quadratic running time, one has to be careful already. We are still in the polynomial time regime here. So quadratic is polynomial time. Cubic, and that's the last column here, is also polynomial time. But here you see that with our computer with 1 million instructions per second, an input that is taking 1 million integers on input is already taking 30,000, almost an astronomical amount of time. Okay, exponential running times. So what actually here matters is the base. So I mentioned factorial. Factorial actually grows worse than any exponential. But you will see that I said that we would only consider efficient algorithms. In some sense, that's not really true. If you limit the input size, so don't go above 100 unless you have a really tiny base of your exponential. Uh, so you see, and when I computed um, this table, I was using hardware floats to compute the final result, and it resulted into infinity, so arithmetic overflow with the hardware floats. So this is to give somehow an impression on why we actually care about the difference between polynomial running time even in different powers of the monomial, and also why we really want to be careful with brute force algorithms. It's okay to use brute force algorithms, but and certainly for testing purposes, if you're a practical minded person, might be very good to do that, but limit the input size. Okay, and limiting the input size is actually something we do not do. We are in a theoretical setup, so we can scale up, and we will focus on asymptotic growth. So let me introduce this with an example. Here we have two functions, P and Q. You could imagine that these are the running times of two processes, P and Q, two algorithms P and Q. And we observe the running time. So for one instance, P is way faster than Q. If we then double the input, then you see, and notice between 4 and 8, that within P, doubling the input, the running time quadruples is kind of a sign of quadratic growth. P actually um, is quadratic growth. So in some sense, P for all our inputs, practical wise, would actually be preferable over Q. Also notice that in practice, often you do not know these nice polynomial functions for the running time. These would be observations. So if you look at the observed running times, look at this table, then you would think that while P grows quadratically, Q goes linearly. I mean, we double the input, and even from 128 to 256, we are about doubling the input size. So actually, we would actually prefer Q from an asymptotic perspective. Although a practical person might argue, no way. You see that in all instances that we tried in the running of our algorithms, P was actually better than Q. Um, so notice that we want to decide which algorithm is more efficient than another. Um, Here is the plot. So if we look at beyond 256, so the running times were clearly where the P was much faster than Q, twice as fast. Uh, but actually, it starts to revert. So after 1000, you will see that there is a crossover point where noticeably the blue line, which is the process P, takes way more time than the red line. And it will be we noticed that P was, even for 256, was about twice as fast than Q. But we will see that in the limit, and actually this is the point that I would like to motivate here. If we are going to look for large inputs, so how does our algorithm scale? Q will be the winner. Q will be the preferred algorithm to use. Okay, so plots, pictures say often way more than 1,000 words, but let's make this formal. We will make this formal with the limit definition. So here is the limit notation where we look over the ratio P over Q. And here in the limit, we will observe that the limit as n goes to infinity, that limit is 2. And that 2, and it's not a coincidence, the 2 is actually the coefficient of the ratio of the coefficients, the leading coefficient of P over the leading coefficient of n, of Q. So this is already an indication why in the definition of polynomial time we worked only with the leading monomials. Q has a very high startup cost, so you could interpret the constant coefficient as the startup cost. So even if you don't do anything, process Q will take that many time compared to the startup cost of P, which is very, very tiny. But the startup cost evaporates. So I'm also trying to motivate why we have here the language that we only consider the values of the input size after a sufficiently large constant. So we let n, and actually there is still a typo here, so let me try to fix this. So the little n should actually have been replaced by the capital N. Okay, we will make this formal. So in the limit, what does this mean? It means that there is an epsilon, and epsilon is a positive but arbitrarily small positive constant, so that once you go beyond n naught, and that's for any epsilon, there exists a constant n naught independent of n, so that after all values for n, the ratio of p over q is actually equals to within that epsilon. Epsilon is actually controlling the accuracy. So you could say after some certain time, the process P will take twice the amount of the process Q. Okay, bottom line, if we talk about polynomial time, we can therefore restrict to the leading term in that polynomial. Constants do matter, certainly in practice. The constants here in front of the leading monomial matter. So if you compare two polynomials of the same degree. Obviously, and we will make this again very formal, obviously if you have higher degree polynomials, then the higher degree polynomials will always take longer than to grow actually faster than the lower degrees. Okay, notation. So we are interested in the worst case running time. That's why the big O notation matters. So if we stick with the examples of the P and Q, we say that both P and Q, they actually are going to be running in quadratic time. So as far as the asymptotic cost goes, the fact that they are uh, that one is twice as fast as the other, it certainly matters in practice. But when we compare the orders of running time, they are the same. So we say that for two functions, that one function, so t is the time, the worst case running time, and f is some function. We say that the time is of the order of that function if there is a constant independently of the input size, such that, and here is again a typo, I was careful to make the distinction between input size and dimension of the problem. So as the input size grows to infinity, so what does that mean? That there is another fixed constant value, there's some threshold. After some, after that threshold, the time is bounded by that constant and the function f. So what is that function f? Well, that function f here is the n square. So that's important here. So in the example, the capital T is either P or Q. The f of n is n square. So constants do matter, but in practice, but here for asymptotic growth, we are interested in the exponents of the monomials. So this is another simplification, another uh, idealization of the problem. Notice that we will have lower bounds as well. So every linear function is also of order quadratic time, although that doesn't seem quite right. So we will also define lower bounds. Okay, time for a first exercise. We have two functions where one function is of the order of the other function. Is if you square the first function, is it so that the square of the function f is of the order of the other function g? Is that the case? I will say here, use the property that the square is a monotone increasing function. So that's actually the punchline of why this is most likely to be true, although I still want to open the door for doubt, because it's not obvious, perhaps, if you need a proof. So the purpose of this exercise is that you make yourself familiar with the definitions. And at some point you will have to use the property that if you evaluate the square at two numbers, if the first number is smaller than the second, so f is smaller than g, then the square of the first number will also be smaller than the square of the second number. So that's kind of the intuition, knowing from long time mathematical practice how a square function looks like. And we've seen two plots already of square functions. Okay, make this exercise. We are in this course doing an analysis, so that means a formal, mathematically rigorous description. Okay, mainly we are interested in the big O, because if algorithms run faster, we actually, the better, but big O's are really bad. Sometimes we actually are interested in asymptotic lower bounds. So there is the big omega. Why are they important? Sometimes the output size is quadratic. So if you want to get to a quadratic algorithm, you start enumerating things and you want in your output all possible pairs. If you consider again the stable matching algorithm, if you want to compute all possible pairs, uh, list all possible pairs of applicants and employers, then you will have quadratic time. Here is an example again. So we have a running time function, and then we have another function, and we want to indicate that the running time is of the lower bound order of the big omega of that function. And here you see the formal definition. This also can be expressed in function of a limit. So at some point, so I will give examples of that. So we actually have already seen this with the ratio. What actually this means that there is a constant so that the ratio of these two is actually bounded. I'm sorry, I'm running ahead of time here. Um, I'm confused. I hope I will not have confused you. But let me point out again the main ingredients. So there is the constant c and the constant n naught. So for this constant c, the function is actually the running time function is larger than the constant time the function f for some threshold and not. Now I realize I have the example there. It's actually not obvious that the running time has the addition, or actually it is obvious, I'm so sorry. So since they are the plus signs, you can actually clearly say that the n is positive. Okay, I'm halfway in this recording. You can see that it's time for me to start to conclude, but with one more very important definition. That's the big data. And actually, if you want a good algorithm that is of high quality, which means it behaves as expected, you always have the same running time, then actually you want a big data. So here is the big data. Because we have the big omega and we have the big O already formally defined, the bottom line definition is very clear. But here you see the same reasoning I had for the P and the Q. You see that we can make very precise we have a very precise prediction of the asymptotic running time. So it is actually the monomial times that constant. And you can make that arbitrarily precise. So the limit definition of this ratio, the running time over the n square, is actually here explained. So the definition independently of the big omega uh, and the big O can be written independently where you replace the n square with the f of n. So if in this reasoning here, oops, what I'm doing now, if you place in this reasoning here, if you replace, oh, um, I'm so sorry. So if you replace here, perhaps I could continue drawing. Now I'm highlighting. If you replace in the denominator the n square by the f of n, then you would have everywhere where you see the n square, replace it by the fn, then actually you have the formal definition of the big theta independently of the big O and the big omega. Okay, so this is the essence of asymptotic growth, asymptotic upper bounds, asymptotic lower bounds, and asymptotic tight bounds, the big theta. All right, if you have that two functions, the ratio of two functions, and again, I should fix another typo. So we have the capital N here, the input size. If we have that the ratio of two functions is constant, then we have that the function in the numerator is big theta of the function in the denominator. So up to a constant, the running times asymptotically of those two algorithms, capital F, capital G, are actually equivalent to each other. And here you see the limit definition, again with the input size, where we have as the input size grows arbitrarily, if you can let that grow arbitrarily large, you have that you can make that ratio arbitrarily small. So the importance of this proof is that it spells out the limit definition. So the limit definition is a very short way of writing the sentence that is here follows. And it illustrates that the running time of f of the function f, how the function f grows, is a constant times the function g plus some epsilon. So the epsilon is kind of the relative error. So I spell out the definition of the limit, so what this notation means, and then I apply the definition of big theta, showing that we have two inequalities here. One inequality, the less than, satisfies the big O. The less than satisfies the big theta. Okay, I will conclude so with some examples. So this is here where we will resume in the second half of this second lecture. There are some canonical examples of algorithms that let you take the running time. So here in this case, I made again the notational error of little n in terms of capital N, although here in these examples, the dimension typically coincides with the input size. Logarithmic cost is binary search in a sorted sequence, so this explains why sorting is so important. Linear time, finding the maximum in a sequence. So if your sequences of integers are not sorted, then finding the maximum or minimum is linear time. As you may have already seen, sorting cannot be done faster than n log n. So this is why n log n is so important, because of the importance of sorting algorithms. If you want to find the smallest distance between points in the plane with a very straightforward algorithm, there are better algorithms than n square, but an example of geometric algorithm that runs in quadratic time is finding the smallest distance between points. Cubic time is when you look for sequences of sets and look for common elements in there. You can make any polynomial time. So, by the way, if you have taken a course in linear algebra, then a typical example of quadratic time is solving a triangular system with an upper or lower triangular matrix. Cubic time is reducing any matrix to a lower or an upper triangular form. I gave the sets examples because of the way how you can make a problem for any polynomial. And then we have the class of exponential time methods or beyond polynomial time. We will not spend too much time on this, but for completeness, they should be concluded here. Okay, in this first half of the lecture, there's only one exercise, but it is a very important one to make yourself familiar with the limit definitions and the notations. Okay, I stop the recording here.